All right, here we go. So there may be a little bit of glare on there, so I'll read through it. So we've got a washing machine that spins at 635 revolutions per minute. When the motor shuts off, it requires 8 seconds to come to a complete stop, and we're looking for the angular acceleration of the drum. Okay, so yeah, like you just said, we don't have the radius here. So if I wanted to find anything linear, if I wanted to find the linear distance that they travel, the linear velocity, linear acceleration, anything like that, I would indeed need to know the radius because that's what relates the angular to linear. But since we're just asking for the angular acceleration, we should be able to do that just fine. So, first thing that I've got here, this 635 revolutions per minute. I want you to think, what is that? Is that a displacement? Angular? It's an angular because revolutions is a unit of angle measure, but it's per minute. So is that displacement or angular displacement? Is it angular velocity? Is it angular acceleration? What is that?
Oh man.
Well, a revolution is an angle, right?
Around, yeah.
And the minutes is a unit of time. So it's angular displacement divided by time. Think about what's a displacement divided by time?
Is it velocity?
It is velocity. Yep. So we've got an angular displacement in a certain amount of time. That is going to be angular velocity. What's the symbol we use for that?
W.
Omega, but close enough. So omega is 635 revolutions per minute. What do we need that in?
Seconds, right?
Well, we definitely need radians, not revolutions. And then seconds or minutes would be fine. Just our unit of acceleration has to agree. Seconds would probably be better. Since we're dealing with 8 seconds, we need to make sure those agree. So first I need to convert this. I've got 635 revolutions in 1 minute. And so I need to multiply by 2 pi radians in 1 revolution. So that gets me to radians. And then just need to take care of the minutes. 1 minute is 60 seconds. Okay? So my omega in radians per second would be, I'll let you guys figure that out.
I got 66.4, 66.5.
66.5. Oh, do you want to confirm that?
Got you, bro. Six. 60, yep.
What was it again?
66.5.
66.5 radians per second. Okay. And then what other information do I have up here that it gives me?
So when we times that by 8, it just takes 8 seconds.
Well, hold on. We know the time interval
Divide by 8?
is 8 seconds. And what are we trying to find?
The acceleration of it.
Angular acceleration. Okay? We have a formula for angular acceleration. Think about it just like normal acceleration is the change in velocity divided by change in time. Okay? So this is one of those problems where it actually tells you something else that it doesn't really explicitly state, but we can infer from the problem. So notice it started out with this angular velocity, right?
I got it.
But it's accelerating, so this velocity is changing. What's the final velocity? The The washing machine spinning at 635 revolutions per minute. When the motor shuts off, it requires 8 seconds to stop. What is the angular acceleration? So obviously, if there's an acceleration, the angular velocity is changing. It started out at this. What did it finish at? After the 8 seconds?
Zero.
Yes, that's what I want you to get. So what I want you to think here, your angular acceleration is equal to the change in angular velocity divided by your time interval. Okay? So what is the change in angular velocity? It's slowing down, so your final is 0.
So negative 66.5.
Yes.
Shouldn't it be squared on the bottom? Is that correct or wrong?
That is incorrect.
Okay.
Oh, your units will be squared, yes. But it's not like, I thought you meant like t squared. No, it's just the change in velocity divided by the time interval.
Because velocity is meters per second squared, right?
Acceleration is. But this will be different. I'll talk about that in a second. First, let's just divide.
8.31.
Okay, it should be negative
Yep.
8.31. This delta omega, so that's the change in angular velocity. What would this unit be in? Okay, let's go back. What is the displacement in? What's an angular displacement? It's just an angle, right? Radians.
Meters.
Right? So this is radians per second. So you've got to think, we're not in linear. We're not measuring meters here. We don't have a radius. It's just the angle. So this is radians per second.
That makes sense.
So the acceleration is radians per second squared.
Okay.
Yep. So basically think everything that you're used to doing in meters,
Just change it to radians.
change it to radians. Yep. So instead of, so we've got displacement was meters, velocity was meters per second, acceleration was meters per second squared. For angular displacement, it's radians. Angular velocity, radians per second, and angular acceleration, radians per second squared.
Simple.
Okay, so we've got a ball in a computer mouse is 2.0 centimeters in diameter. If you move the mouse 12 centimeters, what is the angular displacement of the ball? Okay. And I'm going to go ahead on this one. I'm just going to go ahead and tell you we're going to have some angular, like the last problem was everything was angular. We had angular velocity and angular acceleration. In this one, we're going to be dealing with both angular and linear. So I'm going to put the formulas up here that relate linear displacement to angular displacement, linear velocity to angular velocity, and linear acceleration to angular acceleration.
Even negative version.
All right, here we go. So I'm going to go through a couple things. A ball and a computer mouse is 2.0 centimeters in diameter. So yeah, be careful there. We know from that that the radius is half of that, so 1 centimeter. Okay. If you move the mouse 12 centimeters, what is the angular displacement? So we're trying to find the angular displacement, which is going to be theta. That's going to be an angle. What is this 12 centimeters? What would that be?
How far it went around the circle?
Yeah, that's actually going to be the linear displacement, okay? Because think about it, and you don't have to necessarily draw this out, but if you imagine, so if
it
you've
makes
got
sense.
a mouse on a pad and you move it 12 centimeters, so I'm going to erase this part for just a second. So imagine just the ball that's inside rolling across the pad. Okay. If I move 12 centimeters just across the pad, that's also going to be 12 centimeters around
Okay.
the ball, right? Okay. So yeah, that linear display, so that 12 centimeters is the linear displacement.
So it's literally.
Yep. So we just need this right here. Now, this isn't standard SI unit of meters, but they're the same unit. So everything should agree there. So I'm just going to plug it in. 12 is equal to R, which is 1 times theta. Theta equals 12. And if those units agree, this will always be in radians. Okay? Yeah, pretty straightforward. I just wanted you to understand that moving 12 centimeters across a flat surface like that, since the ball is rolling, it's going to be the same as 12 centimeters around the surface of that ball. It works the same way for like the linear displacement on like tires. So like if you travel a certain distance on a road, it's the same distance like wrapped around the surface of your tires. So anyway, all right, so that is it there. I will put up your guys' assignment is going to be on page 200.
So our angle is actually just 12.
Yeah, 12 radians.
Makes sense.
Okay, which should make sense because it's actually a radian is a ratio of the radius to, so it's like 12 times the length of the radius wrapped around the circle, which is exactly what it was. So, all right, your assignment is on page 200. We are going to do, for sure, we're going to do 1 through 4. Let's just do 1 through 4 for today.
Alrighty.